Good morning. Today we'll start with open channel flow. Open channel flow implies flow in channel open to the atmosphere, but flow in conduct is also open channel flow if the liquid does not fill the conduct completely and there is a free space. The pipe we had already discussed. Flow in pipe is driven by pressure, whereas flow in channel is driven by natural gravity. Water flow in river, for example, is driven by the elevation difference between upstream and downstream. The flow rate in the open channel is established by dynamic balance between gravity and friction. Inertia of the flowing liquid also becomes important in unsteady flow. The free surface coincides with the hydraulic rate line HGL and pressure is constant along the free surface, but the height of the free surface from the channel bottom and thus all dimensions of the flow cross section of the channel is not known a priori. It changes along with the average flow velocity. The pressure in a channel varies hydrostatically in a vertical direction when the flow is steady and fully developed. Natural and human-made open channel flow are characterized by a free surface open to the atmosphere. Open channel flow refers to the flow of liquids in channels open to the atmosphere or in partially filled conducts and is characterized by presence of liquid-gas interface called free surface. Most natural flow encountered in practice, such as the flow of water in creeks, rivers, floods, as well as drainage of rainwater, highway, parking lots, and roofs, is the open channel flow. Human-made open channel flow systems include irrigation systems, sewer lines, drainage, ditches, gutters, and design of such system, and important application area of engineering. So this is a constant. This is your velocity curves in an open channel of a tropoidal cross section. So in open channel, the flow velocity is 0 at the side due to the no slip condition. Here velocity is 0, and it is maximum at the, you can say, at the center, or you can say at this point. So, and this is the mid plane, or you can say free surface. So, and you can see furthermore flow velocity also varies in flow direction in most cases. Therefore, the velocity distribution and the flow in open channel is in general three-dimensional. In engineering practice, however, the equations are written in terms of average velocity at cross section of the channel. Since the average velocity varies only with streamwise distance x, v is one-dimensional variable. The one-dimensionality makes it possible to solve significant real-world problems in simple manner by hand calculation, and we restrict our consideration in this chapter to flows with one-dimensional average velocity. The no-slip condition on the channel wall give rise to velocity gradients, and wall shear stress develops along the wetted surface. The wall shear stress varies along the wetted perimeter at a given cross section and offers resistance to flow. The magnitude of this resistance depends on the viscosity of the fluid as well as velocity gradient at the wall surface. Therefore, open channel flow are also classified being steady or unsteady. If flow is said to be steady if there is no change with time at a given location. The represented quantity in open channel flow is the flow depth, which may vary along the channel. The flow is said to be steady if the flow depth does not vary with the time at any given location along the channel. Uniform and varied flows. Flow in open channel is also classified as being uniform or no uniform, depending on how the flow depth y, the distance of the free surface from the bottom of the channel measured in the vertical direction, varies along the channel. So this is distance from the vertical direction, which is y is equal to y into constant, v is equal to constant. So this is uniform flow. The flow in channel is said to be uniform with the flow depth remains constant. Otherwise, the flow is said to be non-uniform varied, indicated that the flow depth varies with distance in the flow direction. Uniform flow conditions are commonly encountered in practice in long straight section of channel with constant slope and constant cross section. In open channel of constant slope and constant cross section, the liquid accelerates until the head loss due to friction effects equal the elevation drop. This liquid at this point reaches its terminal velocity and uniform flow is established. The flow remains uniform as long as the slope, cross section and surface roughness of the channel remain unchanged. The flow depth in uniform flow is called the normal depth yn, which is an important characteristic parameter for open channel flow. The presence of obstruction in channel such as gate or change in slope and cross section cause the flow depth to vary and does the flow to become varied or non-uniform. Such varied flows are common in both natural and human-made open channels such as rivers, irrigation system and sewer lines. The varied flow is called rapidly varied flow. You can see in this case, in this channel, this is your uniform flow, this is your gradually varied flow, and this is your rapidly varying flow. So if flow depth changes markedly over a relatively short distance in the flow direction, So it is called gradually varied flow. If the flow depth changes gradually, the varied flow is called rapidly varied flow. If the flow depth changes markedly over a relatively short distance in the flow direction. So this is your rapidly varied flow. You can say there is a direction change rapidly. And gradually varied flow, if the flow depth changes gradually over a long distance along the channel. You can see this is a gradually varying flow here, and at this point it is gradually varying flow. Because the flow depth change gradually, there is a slope here and here. The hydraulic radius is defined as the ratio of cross section area and a vector parameter. So RH is equal to AC by P. Considering that open channels come with rather irregular cross section, the hydraulic radius serves as characteristic dimension and brings uniformity to the treatment of open channels. Also, the Reynolds number is constant for the entire uniform flow section of an open channel. You might expect that the hydraulic radius would be defined as half the hydraulic diameter, but this is unfortunately not the case. Recall that hydraulic diameter for a pipe flow is dH is equal to 4 AC upon P. Also, this hydraulic radius is used in this equation to find the Reynolds number, which is equal to density to velocity into hydraulic radius upon viscosity. Now we know hydraulic diameter, which is 4 AC upon P, is equal to 4 RH. If you compare this and this, so we see that the hydraulic radius is in fact 1/4 rather than 1/2 of a hydraulic diameter. The roll number based on hydraulic radius is 1/4 the roll number based on hydraulic diameter. So it means in case of laminar we know roll number less than 2000 is pure laminar flow, but in case of open channel roll number should be less than 500 and it is your laminar flow. Also open channel flow is usually turbulent greater than 2500 and transition between 500 and 2500. So laminar flow is encountered when the thin layer of water, rainwater draining off a road or parking lot flows at a low velocity. Wetted parameter includes the side and the bottom of the channel in contact with the liquid. It does not include the free surface and the parts of the side exposed to air. So for example, take the example rectangle. So in this rectangle, you can see wetted parameter is your y here, and the bottom which is v. So this is your wetted parameter, and cross section is y into v. So this is your hydraulic radius in case of rectangular channel. In case of the cylindrical channel, the cross section area is this r square theta minus sin theta cos theta, and parameter is equal to 2r theta. The hydraulic diameter is area of cross section by parameter. This is a trapezoidal channel, and this is for liquid film thickness y. This is hydraulic diameter, which is yb by b, which is equal to y. Fraud number and wave speed. Open channel flow also classified tranquil, critical or rapid depending on the value of dimensionless Fraud number. You can see Fraud number is equal to velocity equivalent to GLC, where L is characteristic length, which is taken to be the depth y for wide rectangular channel. The Fraud number is an important parameter that governs the character of flow in open channel. Fraud number less than 1, supercritical or tranquil flow. Fraud number is equal to 1, critical flow. Fraud number greater 1 is equal to supercritical or rapid flow. For compressive flow, Mach number is equal to velocity upon c, and for open channel flow, Fraud number is equal to velocity upon c0, where c0 represent the speeds at which the small disturbance travel in still liquid. Therefore, in analogy to the Mach number, the Fraud number is expressed as a ratio of flow speed to the wave speed, just as Mach number is expressed as a ratio of flow speed to sound speed. The Fraud number can be also thought as a square root of the ratio of inertia force to the gravity force. This can be demonstrated by multiplying both numerator and denominator of the square of the Fraud number, which is v square by GLC by density into area. So you can see here, if you multiply, it will become inertia force upon gravity force. If Fraud number is less than 1, it means your inertia force are low. A small disturbance travel upstream with a velocity c0 minus v related to stationary observer and affect the upstream condition. This is called tranquil or subcritical flow. But at high velocity flow, when Fraud number is greater than 1, means inertia forces are large. A small disturbance cannot travel upstream. In fact, the wave is washed downstream at velocity of v minus c0 related to the stationary observer, and thus the upstream condition cannot be influenced by downstream condition. This is called rapid or supercritical flow, and the flow in this case is controlled by upstream conditions. And when your Froude number is equal to 1, the flow appears to be frozen on the surface. Also the surface wave speed increases with flow depth by, and thus a surface disturbance propagates much faster in deep channel than it does in a shallow one. Consider the flow of liquid and open rectangular channel of cross-section area AC with a flow rate of V. When the flow is critical, Froude number is equal to 1 and average flow velocity is equal to under GYC, where YC is critical depth. Noting that volume flow is equal to AC into B is equal to AC into under GYC. The critical depth can be expressed as critical depth is equal to YC is equal to V square by G AC square. For a rectangular channel of width B, we have AC is equal to BYC and the critical depth relation reduces to. So critical depth rectangular, it will reduce to this. So you can see here, this is subcritical flow. When your Froude number is less than 1, then your Y is greater than YC. And this is for supercritical flow. When your Froude number is greater than 1, then your YC is greater than Y. Speed of surface waves. We are all familiar with waves forming on the free surface of ocean, river, lake, even swimming pool, but we will barely notice it. Some are smooth, some are break on free space. We basically understand the wave motion is necessary to study certain aspects of open channel flow. An important parameter in study of open channel flow is the wave speed C0, which is the speed at which a surface disturber travels through a liquid. Consider a long channel, wide channel that initially contains a still liquid of height y. So this is your height of liquid, still liquid. One end of channel is moved with the speed del v, generating a surface wave of height del y, perpetuate a seat of C0 into the still liquid as shown in figure. Now consider the control volume. Now consider a control volume that encloses the wavefront and moves with it as shown in figure. So this is your control volume here. To an observer traveling with the wavefront, the liquid to the right, this liquid, will appear to move toward the wavefront with a speed of C0, and liquid to the left appears to moving away from the wavefront with C0 minus del V. Of course, the observer would think the control volume that encloses the wavefront is stationary and it is a steady flow process. Now apply the mass balance and continuity relation for the control volume, this that mass coming into the system must be equal to mass leaving the system. Now mass coming into the system is equal to your density into gravity into this y into b, which is perpendicular to your screen, and mass leaving is equal to density into velocity, this is velocity, and height is equal to y plus del y into b. And on solving you will get del v is equal to C0 del y by y plus del y. We make the following assumptions. The velocity is nearly constant across the channel, and thus the momentum flux correction factor beta 1 and beta 2 are 1, and the distance across the wave is short, and thus the friction at the bottom surface or air drag at the top are negligible. The dynamic effects are negligible, and thus the pressure in the liquid varies hydrostatically in the terms of gauge pressure. Now here P1 is equal to density to G into H average. Now H average is, in this case, is Y by 2, because force fluid is not placed at Y altitude, it is placed throughout this height. We will take average, which is Y by 2, and in this case it is Y plus delta Y by 2. So this is P2 is this. The mass rate is constant with M1 is equal to M2, which is equal to density into C0 into Y into B. So this is your cross section area, this is your velocity, and this is your density. There are no external force in the body, and thus the only force acting on the control volume in alternate acceleration are pressure forces. The momentum force is equal to summation F is equal to this in the x direction becomes a balance between hydrostatic pressure force and momentum transfer. So this is your total force P average into area, and this is the force at this cross section, and this is force at this cross section. Okay, and we know this force is greater than this force, that's why fluid is moving in this direction, and it is must be equal to the mass into velocity minus mass into velocity. Now put the value of velocity here and here, put the value of pressure and pressure, you will get this equation on solution. Now if you combine this equation and the continuity equation, which is this is a continuity equation, and if you combine these two, you will get this relation here. Therefore, the wave speed is proportional to the wave height, delta y. For infinitional surface waves, delta y is much less than y, and thus C0 is equal to under gy when your delta y is very small. Therefore, the speed of infinitional surface waves is proportional to the square root of the liquid depth, which is under y. Again, this analysis is valid for open channel, shallow water bodies, and not for deep ocean. The wave speed can also be determined by using energy balance relation instead of momentum equation. Note that the wave eventually die off because of viscous effect that are neglected in the analysis. Also, the flow in channel of round rectangular cross section, the hydraulic depth defined is this, where L is the top width of the flow section, should be used in calculation of Froude number in the place of flow depth y. We know experience that when a rock is thrown into lake, the concentric waves that form propagate in all directions and vanish after some distance. But when rock is thrown into river, the upstream side of wave moves upstream if the flow is tranquil or subcritical, and moves downstream if the flow is rapid or supercritical, and remains stationary at the location where it is formed if the flow is critical, means V is equal to C0. Take example of sluice gate as shown in figure. So you can see the flow is subcritical flow here, and it will become supercritical, then again it will become subcritical flow. So you can see at this position, this is called hydraulic jump, which you can see in the sluice gate. The liquid approaches the gate with subcritical velocity, but the upstream liquid level is sufficiently high to accelerate the liquid to a supercritical level as it passes through the gate, just like a gas flowing into converted hydrogen nozzle. But if downstream section of the channel is not sufficiently sloped down, it cannot maintain the supercritical velocity, and liquid jumps up to the higher level and with a larger cross section area, and thus to a lower supercritical velocity. Finally, the flow in rivers, canals and irrigation system is typically subcritical, but the flow past sluice gates and spillways is typically supercritical. Specific energy. Consider the flow of liquid in a channel as a cross section where flow depth is y, this is depth of flow. The average velocity is v, and the elevation of this channel from the reference datum is z. For simplicity, we ignore the variation of liquid speed over the cross section and assume the speed to be v everywhere. The total mechanical energy of the liquid in channel in terms of H is equal to head is equal to Z. This is your pressure upon rho g. This is your y, which is the height of the fluid in the channel. This is your kinetic energy in terms of when you divide by 2g. The unit of this is in meter. So we had in terms of head, it is equal to z plus y plus v square by 2g. Now in most of case we will consider z is equal to 0. The intrinsic energy of the fluid at a cross section can be represented more realistically if the reference datum is taken to be the bottom of the channel. Then the total mechanical energy of a fluid in terms of heads becomes the sum of the pressure and dynamic heads. So total energy becomes Es is equal to this your y and this your this energy, which is the pressure and dynamic heads. Now we know volume fluid is area of cross-sectional channel into velocity, and area of cross-sectional channel, say in this case, is the area perpendicular direction of the flow of this fluid, which is y, and b into the screen of your computer. So it is yb. From here you can find velocity in terms of volume flow rate, and you can replace this velocity in this equation. You will get this equation, which is y plus volume flow rate divided by g into v square into y square. So this is your variation of specific energy with the depth y for a specific flow is given. If volume flow rate is constant, v is constant, you will get this equation here. Es is equal to y, this line. So the distance from the y-axis to a point on this curve, this represents specific energy Es, which is y plus v square by 2g. This is v square by 2g, and this is your y. So this represents your specific energy. The part between y line and the curve correspond to dynamic head. So this is your dynamic head or kinetic energy of the liquid. This is part between Es and this y line. Now if you put y0 here, you can see this Es tends to infinity. Also you can see in the graph, when your y is 0 at when your y tends to 0, your specific tends to be infinite. Also if y tends to 0, you can see in this equation your velocity tends to infinity. You can also see here at this point your energy is almost equal to the y. This is your specific energy, because when your y is very large at this point, say when your y increase, if your y increase, this term will decrease and it will negligible as compared to this term at high y. So your specific energy is a function of y only at higher y. Also if you increase y, your velocity will become small, and so the kinetic energy. So this part will be decrease as your y will increase. You can see here the difference between pink line and this shaded line will decrease, and your specific energy is almost equal to this y. Now see in this graph, your specific energy is minimum at this point, and this point is called your critical point, and yc your depth corresponding to the critical point. Now if you put this value yc in this here, what you will get, critical velocity, means if you use this yc in this equation, you will get critical velocity. Now correspond to this in the energy minimum, this point is called at this point flow number is equal to 1. So there is minimum specific energy E minimum required to support the specific flow rate V dot. Therefore Es cannot be below than Es minimum for a given flow rate, and this is called supercritical flow number greater than 1, and this is called subcritical flow number less than 1. You can see this is your horizontal line and it intersects at one point of the curve. It means corresponding to a particular value of depth, there is a corresponding specific energy of fixed value. But if you check in this region, so if you draw a vertical line, it will intersect at 2 points, at this point, at this point. It means the flow has two depths corresponding to the same specific energy. So it means at this point your depth is different, at this point your depth is different, but energy is same. These two depths are called alternate depths for flow through sluice gate with negligible friction loss. The upper depth corresponds to the upstream flow and the lower depth to the downstream flow. So if you are near to this point, which is your correspond to the energy minimum point, you can see for the same corresponding energy, a small change in specific energy near the critical point causes a large difference between alternate depths and may cause violent fluctuation in the flow level. You can see small change in energy will lead to the large change in the depth, which will cause fluctuations because slope at this point is very large. Therefore, operation near the critical point should be avoided in the design of open channels. Now at this critical point, you can see the slope is changing. It means if you take the derivative of this with respect to y, this must be equal to 0. So at this point your slope is 0. Now if you take the derivative of this and equate to 0, you will get this equation here between yc is equal to v dot square by dv square raised to power 1 by 3. Now this instead of y you can use y critical, because this minimum energy will occur at critical flow depth, which is y in c in this case. So this is your yc here. Now if you put the volume fluid value into this equation here, you will get the critical velocity is equal to under gc by c, and if you put this value in this equation, so you will get Froude number is equal to 1, which is the Froude number at this point, corresponding to this point. Now if you put the velocity here vc, critical velocity, you will get energy minimum correspond to that critical velocity, means put the value of vc in this equation, and by putting this, when we know vc is equal to under g by c, when you solve this, you will get minimum energy specific energy, that is 3 by 2 yc. So in uniform flow, the flow depth and the flow velocity, this is your flow depth and this is your flow velocity, and thus the specific energy Es remains constant. The head load is made up by the decline in elevation. In non-uniform flow, however, the specific energy may increase or decrease depending on the slope of the channel and the friction losses. Water is flowing steadily in a 0.4 meter wide rectangular open channel at a rate of 0.2 meter cube per second. If the flow depth is 0.15, determine the flow velocity if the flow is subcritical or supercritical. Now we know velocity is equal to volume flow rate by area of cross section. Volume flow rate is equal to 0.2 meter cube per second, and area of cross section is this y into b. This is your b, this is y. So your average flow velocity is equal to 3.3 meter per second. Now this is the relation for critical depth yc. So yc is equal to volume flow rate square by gv square raised to power 1 by 3. So you will get 0.294 meter here. So actual flow depth is 0.15 meter, which is less than the critical depth. It means your flow is supercritical, because our depth is less than the critical depth. Now we know this is your specific energy equation. Also it is having y square. So there must be two values of y which will satisfy this equation. As in quadratic equation, we have two solutions, so same there are two value of y which will satisfy this equation. For actual case, our actual depth is 0.15 meter, and velocity volume flow rate we had calculated. This is your gravity into b square into y square. So our specific energy is 0.713 meter. Now we will find the corresponding depth in the second case, that is Es2 and Est will be same, means there are two energies with same value correspond to different depth. So there are two depths but energy is same at this point and this point. So put this value of energy, specific energy, in this equation, and we know another parameter, but this time keep this y2 unfilled. You will get this equation. From here you will get a value of y2 which is 0.69 meter. So we had two values of y. One is 0.15 meter which is actual case, and second, by keeping the energy same, specific energy, we had second value which is 0.69 meter. Therefore, if the character of flow were to change from supercritical to subcritical while holding the specific energy constant, the flow depth would rise from 0.15 to 0.69 meter. Continuity and energy equations. Open channel flow involve liquid whose densities are nearly constant and does one-dimensional steady flow, and apply conservation of mass, or continuity equation can be expressed as, so volume flow rate is equal to area of cross section into velocity which is constant. So that is the product of flow, cross section, and average velocity will remain constant, means you can write in this for two sections 1 and 2. AC1 V1 is equal to AC2 V2. Area and velocity product remains constant, which is identical to steady flow continuity equation for liquid flow in pipe. Now consider a point A in the liquid at a distance A from the surface, free surface, and thus distance YA minus A from the bottom of the surface. Now velocity at point A is equal to VA and elevation at point A is equal to, what is elevation of point A, is equal to Z plus Y minus A. So Z is your elevation of A, which is Z plus Y minus A. Now what is the pressure at point A? The pressure is due to the fluid which is above point A, which is your density to gravity into A. And what is your velocity VA of the fluid? That is V. Now put into the total energy of the liquid in terms of head. This is your total energy of liquid in terms of head. HA is equal to ZA, which we had calculated. PA by rho G. PA is your pressure, which is due to this liquid above this point A. And this is your kinetic head. Now put the value of Z in this equation and put the value of PA, pressure, in this equation. You will get this equation here. So these three energies will add, and this is your energy line which is here. Now you can see this energy is independent of point A at that cross section. In this equation there is nothing here which is different, that this is correspond to point A. This is independent of A. The energy at point A, or you can say the total energy of liquid in terms of head at point A, is equal to constant, which is independent location of point A at that cross section. So this is a cross section and independent of this point A at that cross section. Therefore total mechanical energy of liquid at cross section of an open channel can be expressed in terms of heads, which is where Y is your flow depth, Z is your elevation of the, and V is your average velocity, flow velocity. Now you can generalize this equation for 2 points, Z1 Y1 plus V1 square by 2G plus Z2 Y2 plus V2 square by 2G plus HL. The head loss due to frictional effect is expressed in the pipe flow, which is your HL. HL is given by this equation which we have already discussed. You can place this this DH, which is your hydraulic diameter with the hydraulic radius, and this is the relation we had already derived it. Now flow in open channel is gravity driven, and thus a typical channel is slightly sloped. The slope of bottom of the channel is expressed as S0, which is tan alpha, which is equal to Z1 minus Z2 by X2 minus X1. Now this X2 minus X1 is equal to length of the channel. So this is your flow of the liquid in this channel. This is X1 and this is X2, one cross section 2, and this is your slope. Now suppose slope S0 is equal to constant. If the channel bottom is straight, in this case which is straight, so that the bottom slope is constant, we know S is constant. The vertical drop between section 1 and 2 can be expressed as Z1 minus Z2 is equal to S0L. You can rearrange this equation, Z1 minus Z2, and if S0 is constant, so Z1 Z2 minus is equal to become S0L, and you can replace here Z1 and Z2 in terms of S0L, so you will get this equation here. Now if you represent this energy, we know energy on the both side section is same. This is the constant energy line, same energy at the both section. This is V1 square by 2, this is Y1, and this is your Z1, which is expressed in terms of S0L, and this is your energy at this point, head loss HL plus V2 square by 2G and Y2. In the design of open channel system, the bottom slope, this S0, is selected such that it provides adequate elevation drop to overcome friction head loss and thus to maintain flow at desired rate. Therefore, there is a close connection between the head loss and the bottom slope. Means this slope S0 and head loss has a close connection, and it makes sense to express the head loss as a slope. We can express this head loss even in terms of slope. This is done by defining a friction slope.
which is defined as SF, which is HL by L. Now you can replace this HL in terms of SF, which is friction slope. So this is your energy equation in terms of slope, friction slope, and your slope of this channel, which is constant. Now take a special case where your HL is equal to Z1 and Z2. So if HL is equal to Z1 and Z2, you can replace in this equation. Now HL is equal to S0 L. Now you can see HL is equal to S0 L, and we had here HL is equal to SFL, which will conclude that SF and S0 are same. Note that the friction slope is equal to the bottom slope when the head loss is equal to the elevation drop. That is, SF is equal to S0 when HL is equal to Z1 minus Z2. You can interpret this. So this figure also shows this energy line, which is distance Z plus Y plus V square by 2G, total mechanical energy of liquid expressed as head, above this reference datum. The energy line is typically sloped. Here you can see energy line is sloped down like the channel. As the channel is sloped, energy line is sloped. The vertical drop being equal to the head loss. Now you can say this slope, you can say the drop in this energy line is equal to head loss, and from this point to this point there is a HL loss. So this is the drop in the energy line. Note that if there were no head loss, if there is no head loss, this HL is missing, the energy line would be horizontal even when the channel is not. If there is no head loss, energy line will still remain constant as this even the channel is not. The elevation and velocity heads means this is your elevation head Z plus Y, and this is velocity head, would able to convert to each other during a flow in this case, but there is some would remain constant, that is this. Or you can say if there is no head loss, this term and this term, they will interchange to give you new terms, but overall sum will remain constant. So uniform flow channels. Flow in channel is uniform if the flow depth remains constant. So uniform flow conditions are commonly encountered in practice in long straight runs of channel with constant slope, constant cross section, and constant surface lining. In the design of open channel, it is very desirable to have uniform flow in the majority of the system. You can say a flow depth in a uniform flow is called normal depth. This is your Yn, Y1 and Y2 are equal. Y1 and Y2 equal, which is equal to Y1 n, and V1 is equal to V2, which is equal to Y0. So this is in case of uniform flow, means your depth will remain constant, your velocity will constant throughout the channel at two sections. The flow remains uniform as long as the slope, means as long as your slope is constant, your flow remains uniform and surface roughness of channel remains unchanged. Now you can see this is your slope S0, which is tan alpha is equal to constant. Now x2 minus x1, this can be written as L cos alpha, where L is this length of the channel. This is the length of the channel. And if cos alpha is very small, if slope is very small, you can still write x2 minus x1 is equal to L to simplify. Also in this case, head loss is equal to elevation loss, which is equal to Z1 minus Z2 is equal to S0 L. When the bottom slope is increased, when you increase this S0, the flow velocity increase, this flow velocity will increase, and the flow depth decrease, so this flow depth will decrease. Therefore, a new uniform flow will be established with a new flow depth. The opposite occurs if the bottom slope is decreased. So during flow in open channel of a constant slope S0, constant cross section area AC, and constant surface friction F, the terminal velocity is reached, and thus the uniform flow is established when the head loss equal to the elevation drop. So therefore head loss is equal to, we had this. Now we know head loss is equal to elevation drop. So measure head loss is equal to, must be equal to Z1 minus Z2 for uniform flow or uniform velocity. Now we know that this is equal to SF into L. We had already calculated here. In this case, This is SF is equal to L, or it can write as S naught L. Now you can replace this head loss with S naught L and put the value of this RH in terms of DH. You can write this 4 RH. Now check this second relation. From this relation you can find V naught velocity, which is equal to C under S naught RH, where C is your called Chassis coefficient. Its value is equal to under AG by F. And if you multiply this by cross section area, you will get volume flow rate corresponding to the uniform flow when your head loss is equal to S naught L. Now the Chassis constant is the dimensionless quantity. This is your dimensionless quantity, and its value range from about 30 for small channel with rough surface to 90 for large channel with smooth surface. Now in this Chassis coefficient, this F is called friction factor, which you can calculate from the Moody chart or the Colebrook equation for the fully rough turbulent limit when your load number tends to infinity. So this is your friction factor. If you row this is your surface roughness, if you row the mean surface roughness, you can find this value of friction factor. You can put here and you can find Chassis coefficient. Now you can also this relation instead of this C here, which is here under root 8G by F, you can also replace this C with this C is equal to A by N RH raised to power 1 by 4. Now this is called, now this N is called Manny coefficient, whose value depends on roughness of channel. Now if you substitute this C value into this equation here and here, you will get uniform flow velocity in terms of C, which is this is your velocity in terms of A, N, and this hydraulic diameter and S naught. The factor is A is dimensionless constant, whose value in SI unit is 1 meter raised to power 1 by 3 per second. Note that the bottom slope S naught and the Manny coefficient N are dimensionless quantities. So this N and S naught is also dimensionless, while RH is expressed in meter, and this will give you velocity in terms of meter per second. There are experimental determined values for N for different materials. N varies from 0.01 for glass to 0.150 for trees. So the variation in the N is very large, so it is considered uncertainty in the value of N, especially in natural channels, as you would expect, since no two channels are alike. The scatter can be 20% or more. Also the coefficient N depends on the size and shape of channel as well as the surface roughness. Critical uniform flow. So when your flow number is 1, this is your critical flow, and thus flow speed equals to the wave speed. Vc is equal to under Gcy. When Yc is the critical flow depth defined previously. So when the volume flow rate, the slope S0 and the Manny coefficient N are known, the normal flow depth Y can be determined from Manny equation. So if you know volume flow rate, if you know S0, and if you know Manny coefficient, A is given, while cross section is not given. And along with this you can use one more equation, that is you can calculate critical depth if you know the volume flow rate and if you know cross section area. But cross section area is not missing. However, since cross section area and your RH, which is your hydraulic radius, are both function of Yn and requires a numerical or trial and error approach to solve. If Yn is equal to Yc, the flow is uniform critical flow, and the bottom slope S0 is equal to the critical slope Sc in this case, and Yn is known instead of the volume flow rate. The flow rate can be determined from the Manny equation and the critical flow depth from equation. Now when your flow is critical, during this flow S0 is equal to S critical, Yn is equal to Y critical. Replacing volume flow rate and S0 in the main equation Y, volume flow rate this. So put values in this equation for the velocity, for the volume flow rate which we had given, which is this, and on solving you will get this relation. This is your critical slope. So critical slope is at this point, critical point.
Now you can replace this hydraulic radius in terms of YC. Then you will get this equation here.
So water is flowing in a VD vacuated or channel of trapezoidal cross section with bottom with 0.8 meter, trapezoid angle of 60 degree theta and bottom slope angle of 0.3. So this is alpha. So this is slope alpha. If the flow depth is measured to be 0.52 meter, find the flow rate of water through the channel. What would your answer be if the bottom angle were 1 degree? Means if instead of 0.3 we use 1 degree, what would be the flow rate in this channel?
We have to find hydraulic radius of the channel, which is cross section area upon perimeter. Now for this case, what is cross section area and what is perimeter, that you can calculate from the table. So this is your trapezoidal channel. You can calculate cross section area and perimeter from this equation. You can find hydraulic radius. Theta in this case is 60 degree. We know bottom slope, which is tan alpha, is equal to this. Now what is volume flow rate, which is equal to A by N, AC, RH, S0. This is your volume flow rate, which is 0.6 meter cube per second. Now change this alpha with 1 degree. You will get a different slope and put into this equation. You will get a second volume flow rate, which is equal to 1.1 meter cube per second. Best hydraulic cross sections. Open channel systems are usually designed to transport liquid to a location at a lower elevation at a specified rate under the influence of gravity at the lowest possible cost. Noting that no energy input is required, the cost of an open channel system consists primarily of the initial construction cost, which is proportional to the physical size of the system. Therefore, for a given channel length, the perimeter of the channel is independent of the system cost, and it should be kept minimum in order to maximize the size and thus the cost of system.
So we have to minimize this perimeter.
This means we have to minimize this parameter
to decrease the resistance in the channel. Another prospective resistance to flow is due to wall shear stress, tau wall, which is, you can say, between the fluid and wall, and which is equivalent to the wetted parameter per unit channel length. Therefore, for a given flow cross section area, the smaller the wetted parameter, the smaller the resistance force. Means if this parameter is less, the lesser is the resistance force. So the best hydraulic cross section for an open channel is a semicircular one, since it has the minimum wetted parameter, this for a specified cross section, and thus minimum flow resistance. There is another perspective for a specified channel geometry with a specified bottom slope S0 and surface lining, and thus the roughness coefficient is given. The flow velocity is given by Manning formula, which is this. Now you can see velocity is proportional to RH square, hydraulic radius square. It means we have to maximum this factor, and to maximize this factor RH, we can maximize by decreasing the parameter. In order to maximize the average flow velocity or the flow rate per unit cross section area, we have to maximize the hydraulic radius and minimize the parameter. Thus we conclude the best hydraulic cross section for an open channel is one with the maximum hydraulic radius, or equivalent the one with minimum wetted parameter for a specified cross section.
In case of rectangular channel, this is your hydraulic diameter, which is equal to AC upon parameter, which is by P by B plus 2y.
Now if you put y is equal to b by 2, you will get hydraulic diameter as maximum value, which is possible in case of rectangular channel. The slope of, or you can say the shape with the minimum parameter per unit area is circle. Therefore, on the basis of medium flow resistance, the best cross section for an open channel is semicircle one. Now, rectangular open channel of width b and flow depth y for a given cross section, the highest flow rate occurs when y is equal to b by 2. Let's see how. So you can take example where your rectangular channel of niched concrete n is equal to this and width b and flow depth y with a bottom slope of 1 degree. Determine the effects of aspect ratio yv on the hydraulic radius rh and the flow rate volume is equal to per unit cross sectional. That is RH and volume flow rate are evaluated from Manning formula. The results are tabulated and plotted. You can see in this table your aspect ratio versus your hydraulic radius and flow rate is given. You can see your flow rate is increasing with increase in aspect ratio, but at this point when your aspect ratio is 0.5, your flow rate is maximum. It will increase, and then beyond this point, if you further increase the aspect ratio, your flow rate starts to decrease further. And you can see here the flow rate plotted versus aspect ratio. At 0.5 aspect ratio, your flow rate is maximum, and beyond that 0.5 aspect ratio, your flow rate starts to decrease. The variation of flow rate in rectangular channel with respect to ratio, where aspect ratio r is equal to y upon b and cross section here 1 meter square and your s0 is 1 degree. So these results confirm that best cross section of a given shape is the one with the maximum hydraulic radius, the one with the minimum parameter. Rectangular channels consider equal flow in an open channel of rectangular cross section of width b and flow depth y. The cross-sectional area and the wetted parameter flow section are AC is equal to y into b and parameter is equal to b plus 2y. So now solve these two equations for parameter. So find b from this equation, which is AC upon y. This is parameter is equal to AC upon y plus 2y. Now if you take the derivative of this derivative, you will get dpy dy, which is equal to minus AC by y square plus 2 is equal to minus Vy y square plus 2 is equal to this. Now parameter should be maximum, it means derivative should be equal to 0 for the maximum condition. So derivative is equal to 0, put this is equal to 0, you will get y is equal to b by 2. Means best hydraulic cross section in case of rectangular channel is y is equal to b by 2. At this your parameter is minimum. Now for minimum, put dp by dy is equal to 0 and solving for y. You will get y is equal to b by 2, which is best hydraulic cross sectional for rectangular channel. Same you can take for trapezoid channel. This is area of cross section, which is v plus y by tan theta into y. So area of cross section is this here, and parameter in this case is equal to b plus 2y by sin theta. Now find the parameter and take the derivative and again put equal to 0. When you solve this, you will get this relation. This is best hydraulic cross section for trapezoidal channel for the minimum parameter. Now if you take the derivative of p with respect to d theta and put is equal to 0, means we have to find angle which will give you the minimum parameter. So when you do dp by d theta is equal to 0, you will get theta is equal to 60 degree, and when you substitute, you will get y is equal to b sin theta by 2 minus 2 cos theta. You will get y is equal to under 3 by 2b. Now you can find this length of the side edge, which will come as b. It means this bottom end must be equal to the side edge. It means parameter becomes 3b, b plus b plus b. So you can see this is not surprising since hexagon closely approximates a circle. So this is actually a half hexagon, and a half hexagon has the least parameter per unit cross section area of all trapezoidal channels. Consider steady flow in rectangular open channel of width b. and assume any variation in the bottom slope and water depth to be rather gradual. We again write equation in the terms of average velocity V and assume the pressure distribution to be hydrostatic. The total head of the liquid at the cross section is at ZB. The total head, this is equal to ZB plus Y plus V square by 2G. Now differentiate this equation with respect to x. You will get dH by dx is equal to dy dx of this, which is equal to dzb by x plus dy by dx plus v by g into dv by dx. Now this is your friction slope and this is your bottom slope of this channel. Now you can see this is your represent head and this change dHL. This is equivalent to the loss in head, means dHL is equal to dH. This dHL is equal to the loss in head, because in from x to x plus dx you had dH head loss, say, and from x to x plus dx you had dHL loss. Now this dHL by x is equal to your SF, that is your friction slope. It is negative because your dH is decreasing along this direction, so that's why it is negative here. Now ZB has decreased from this value to Z plus dZB. You can find what is dZB here.
So dZB by dx is equal to minus of slope S0. This is a slope. So S0 minus SF, and when you put in this equation, you replace this with this and you replace this with this, you will get this equation here. The contraindication for studying flow in rectangular channel is V dot is equal to YBV is equal to constant. So if you take the derivative of this for study flow, the volume flow rate of this channel must be same. So take the derivative for study flow and it's equal to 0. So when you take the derivative, you will get this equation here. And from this, dV by dx is equal to minus y v by y into dy by dx. Now put this dV by dx in this equation. You will S0 minus SF is equal to, you will get this equation here. Now careful consideration, this v square by gy is equal to your Froude number. We know that Vy under Gy is the Froude number. So this is your Froude number. So we have this equation here. This is equal to this. On rearranging, you will get dy dx is equal to S0 minus SF by 1 minus Fr square. The general trend of flow, whether it increases, decreases or remains constant along the channel, depends on the sign of dy by dx, which depends on the signs of numerator and denominator. Means if you take the sign of this and this, so Froude number is always positive, so we have to consider these values of S0 minus SF. The bottom slope of S0 is positive for downward sloping, 0 for horizontal and negative for upward sloping. The flow depth increases when dy by dx greater than 0 and decreases dy x less than 0 and remains constant, and thus the free surface is parallel to the channel bottom as in the uniform when dy by dx is equal to 0, and thus S0 is equal to SF. The determination of sign of a denominator is easy. It is positive for subcritical flow when Froude number is less than 1 and negative for supercritical flow when Froude number is greater than 1. In uniform flow, y is equal to y1, noting that head loss increase with increasing velocity and that the velocity is inversely proportional to the flow depth of the given flow rate. So SF greater than S0 and thus S0 minus SF less than 0, and when y less than yn and SF less than S0 and thus S0 minus SF greater than 0 when y greater than yn. The denominator S0 minus SF is always negative for horizontal. S0 is 0 and upward sloping, so S0 less than 0 channels, and thus the flow depth increases in the flow direction during subcritical flow in such channels. Liquid surface profile in open channels, YX. Open channel systems are designated and built on the basis of projected flow depths along the channel. Therefore, it is important to be able to predict the flow depth for a specific flow rate and specific channel geometry. A plot of flow depths gives the surface profile of the flow. You can see here we had a designation by letter SCMH. This is your steep, critical, mild, horizontal, adverse. Each profile is identified by letter that indicates the slope of the channel, by number that indicates the flow depth related to the critical depth YC. So a surface profile is designated by 1. This is numbering system. If the flow depth is above the critical depth and normal depth, this is your normal depth, this is your critical depth, it is above both, so it is noted by 1. And by 2, if your depth lies between, if flow depth is between Yn and Yc, and if 3, if your flow depth is below than the critical flow. Therefore, 3 different profiles are possible for a specific type of channel slope. But for channels with zero adverse slopes, type 1 flow cannot exist, since the flow can never be uniform or horizontal and upward channel. Type 2 flow does not exist for channels with critical slope, since normal and critical depths are identical in this case. Also, the channel slope is said to be mild if Yn greater than Yc. If Yn is greater than Yc, your channel slope is mild. So slope is steep if Yn less than Yc, it is steep, and critical if Yn is equal to Yc. So if these two are equal, so it is critical. And horizontal if slope S0 is equal to 0 bottom slope, and adverse means this case when your S0 less than 0 means negative slope. We have above studied these 3 types of initial positive positions, and we have studied total 5 types of classes of this slope, gives a total of 12 distinct configuration for surface profiles in gradually varying flow. The floor number is also given for each case when floor number greater than 1. So it means Y less than Yc, means here this is Y is less than Yc, as well as sign of slope dy by dx of the surface profile determined from this equation. You can find the dy by dx from this formula here. Note that dy by dx greater than 0, and thus the flow depth increase in the flow direction when both S0 minus Sf and 1 minus Fr square are positive or negative. So otherwise dy by dx less than 1, or you can say less than 0, it is negative. In type 1 flow, the flow depth increase in the flow direction and the surface profile approaches the horizontal plate asymptotically. In type 2 flow, the flow depth decrease and the surface profile approaches a lower Yc less than Yn. So in this case, your Yc is less than. In type 2 flow, this case, the flow depth Y decrease and the surface profile approach lower of Yc and Yn. In type 3 flow, the flow depth increase and the surface profile approach the lower of Yc. So these trend in surface profile continue as long as there is no change in the bottom slope or roughness. Now in the mild channel where slope is less than critical slope, you can see here we had 3 profile M1, M2 and M3, where M1, in case of M1 you can see Y greater than Yn. In case of M2, Y lies between Y critical, Yn. In M3, Y is less than Y critical. So correspondingly floor number is given for these profile and profile slope is given here. You can see dy by dx greater than 0, it means the slope is positive. So this is your profile of the Y. That's why you can see in case of MM, this is the profile of the fluid. Now in the second case, when dy by dx less than 0, it means your slope is negative,
In this case, you can see this is your velocity profile and slope is negative also. The same is here. And in this case, dy by dx is greater than 0. Again, your slope is positive. So this is the profile. It means dy by dx will define your surface profile. In case of steep, yc greater than yn and s0 less than sc. So s1, y greater than yc, floor number less than 1, dy by dx greater than 0. You can say slope is positive. So this is the case. In S2, y lies between y and yc, floor number greater than 1, dy by dx is negative. So in this case, your profile is this, slope is decreasing, which you can see here. The profile of the fluid, it is decreasing, slope is decreasing. Then you can check S3. Now in S3, your y is less than yn. That is possible when your gate, there is some gate, a restriction at the flow of the fluid. So in this case, again your slope is positive. So this is the positive here, dy by dx greater than 0.
Now in case of horizontal, when your yn tends to infinity, s0 is equal to 0, means your slope is almost horizontal. It is horizontal. So H2, 2 belongs to the region, this region 2. Now in this region, your y greater than yc, probably less than 1, dy slope is less than 0. So you can see in this case your slope is negative. You can see also in H2 your slope is like this, negative. And for H3 you can see slope is positive. This is slope is positive. Adverse when s0 less than 0. A2 case when your y is greater than yc, floor number less than 1, dy by dx less than 0. So you can see this is your slope and here this is your slope, A2. For A3, this is the slope. You can say dy by dx greater than 0. So it is positive. So here it is positive. So this is flow through a sluice gate in open channel with mild slope. This is here M1. This is here M3. You can calculate this from, this is M1 and this is M3. Same you can check from here. Flow through a sluice gate in an open channel with adverse slope and free fall. So this is A2, A3 and A2. So this is A2, A3 and A2. You can check also from here with the slope. So flow with an adverse slope cannot be maintained unless the inertia force overcome the gravity and viscous force. So if you have to maintain in uphill direction, so the flow has to overcome inertia and gravitational force. The open channel section. So in this case it involves a steep to less steep slope. The flow velocity in this less steep part is lower and thus the flow depth is higher. When uniform flow is established again, noting that uniform flow with steep slope must be supercritical. So in this case, this is steep slope, it must be supercritical. And the flow depth increase from the initial to the new uniform level smoothly through an S3 profile. You can see here your flow depth increases. And same in case you can see here it is M2, this is S2 because it is in between yn and y critical. Then you had here H3 flow because it is less than, it is a horizontal surface, also it is less than y critical, and then is a hydraulic jump, then it is H2. You can see condition of H2, H3. Here you can see rapidly varying flow and a hydraulic jump. Recall that flow in open channel is called rapidly varying flow if the flow depth change remarkably over a relatively short distance. You can see this is one section, two section. So this is depth here, flow depth, this is depth here, flow depth. So this is your total energy line, this is the head loss. A change in the cross section of a channel is an important reason for occurrence of rapidly varied flow, but some rapidly varied flows such as flow through a sluice gate occur even in regions where the channel cross section is constant. Rapidly varied flows are typically complicated by the fact that they may involve significant multidimensional and transient effects, backflows and flow separation. You can see this is your hydraulic jump if you take this control volume.
Also you can say the energy at 1 and energy at 2 is almost same, means at different cross section energy is same. So y1 and y2 corresponding to this height, which is your flow depth. The flow in steep channels can be supercritical and the flow can be changed to subcritical if the channel can no longer sustain supercritical flow due to reduced slope of the channel or increased friction effects. Any such change from supercritical to subcritical flow occurs through a hydraulic jump. A hydraulic jump involves considerable mixing and agitation and does a significant amount of mechanical energy dissipation. So this is density to gravity to y1. This is the average of this pressure on this phase, and this is the average of this pressure on this phase. We will analyze this by assuming assumptions. The velocity is nearly constant across the channel at section 1 and 2, and therefore momentum flux correction factor beta 1 and beta 2 is equal to 1. The pressure in liquid varies hydrostatically, and we can consider gauge pressure only since the atmosphere pressure acts on all surface and its effect cancel out. The wall shear stress and the associated losses are negligible related to the losses that occur during the hydraulic jump due to the intense agitation. The channel is wide and horizontal. There are no external or body forces other than gravity. So apply the conservation of mass or continuity equation. So it is this m2 is equal to m1. You will get y1 v1 is equal to y2 v2 because density is constant and b is depth of the channel which is perpendicular to your screen. It is constant at both cross section. Now on this volume element, control volume, forces acting are the pressure force from both sides. The momentum equation is equal to this, sum of all forces is equal to summation V10 to mv minus momentum out minus momentum in the x direction becomes a balance between hydrostatic pressure and force and momentum transfer. So this shear force P1 into A, pressure average into A1 on this direction, this shear force, and from this direction your force is your pressure into, which is this, into this area, so which is this A2. Now must be equal to mass into velocity minus momentum into velocity, which is momentum transfer. Now put the value of pressure average which is equal to this and pressure average which is equal to this. For a channel width of B, we have A1 is equal to Y1B, A2 is equal to Y2B, and mass rate are equal. Substituting and simplify the momentum equation.
So when you put the value of pressure here and pressure in this equation, and you put the value of mass flow rate is equal to this into the equation, you will get this equation. Now replace V2 in terms of Y1 by Y2 and V1 from the continuity equation. You will get this equation. Now cancel this on both sides. You will get this equation, and we know this is the Froude number. So this is a quadratic equation of Y2 by Y1, and it has two roots. One is negative and one is positive. Noting that Y2 by Y1 cannot be negative because these two are length or depth, these are positive. So it means we will take the positive root. So when you solve this, you will get this solution Y2 by Y1 0.5 minus 1 plus 100 b square minus 4ac. You will get this here. So this is your depth ratio. We know energy equation for horizontal flow section is this. V2 is equal to this. You can replace V2 in this equation, and we know also Froude number is equal to this. You can find HL, which is a head loss associated with hydraulic jump, which is equal to this. So it means we had find this hydraulic loss in this case due to hydraulic jump. Now say Froude's number is less than 1. We assume this case. Now in this case HL become negative. If you put Froude number less than 1, HL will become negative, which is impossible, which is violation of second law of thermodynamics.
entropy generation cannot be negative. Thus we conclude that the upstream flow must be supercritical for odd number greater than 1 for a hydraulic jump to occur. Means here Froude number must be greater than 1 for a hydraulic jump to occur. So this is the condition for the upstream. Head loss is a measure of mechanical energy dissipated by internal fluid friction, and head loss is usually undesirable as it represents the mechanical energy wasted. But sometimes hydraulic jumps are designated in conjunction with the stalling basins and spillways of dams, and it is desirable to waste as much as mechanical energy as possible to minimize the mechanical energy of the water, and thus it's possible to cause damage. This is done by first producing supercritical flow by converting high pressure to high linear velocity, and then allowing the flow to agitate and dissipate part of its kinetic energy as it breaks down and deaccelerated to subcritical velocity. Therefore, a measure of performance of hydraulic jump is its fraction of energy dissipated. So the energy dissipation ratio is equal to head loss divided by energy of the fluid, which is equal to y1 plus v1 square by 2g, which is equal to this. The fraction of energy dissipated range from just a few percent for a weak hydraulic jump to 85% for strong jumps when Froude number is greater than 9. Hydraulic jump. Water discharged into a 10-meter wide rectangular horizontal channel from a sluice gate is observed to have undergone a hydraulic jump. The flow depth and the velocity before the jump are 0.8 meter and 7 per meter square. Determine the flow depth and the Froude number after the jump, the head loss and the dissipation ratio, the wasted power production potential due to hydraulic jump. So first we have to calculate the Froude number, which is v1 by under g y1. Velocity v1 is given, y1 is given. So it is 2.5. Now which is greater than 1. So therefore the flow is indeed supercritical before the jump. So now you can find the flow depth, velocity and the Froude number after the jump, which is y2. From this equation you can find y2, the flow depth, because Froude number we had Froude number. Now we had y2, you can find velocity v2 from the conservation of mass rate, or you can say continuity equation. Then you can find Froude number. Now we have Froude number 2. Now you can find head loss in this flow jump, hydraulic jump, which is HL is equal to this. This is your head loss, 0.572 meter. Now we can find dissipation ratio, which is head loss upon total energy. Total energy fluid is equal to this at one cross section before the jump. Dissipation is 0.713. So dissipation ratio is 0.173. Therefore 17.3% of available head of the liquid is wasted. The mass rate of water is equal to density into volume flow rate, which is equal to density into B into y1 into v1, where B is your depth perpendicular to the screen, which is 66,000 kg per meter second. Now energy dissipation is equal to mg/hl, which is equal to 314,000 Newton dot meter per second is equal to 314 kilowatt. This energy wasted is 314 kilowatt of power, and you can say this will cause a rise in temperature by this degree for this much amount of water flow rate. Flow control and measurement. The flow rate in pipes and ducts is controlled by various kinds of valves. Liquid flow in open channels. However, it is not confined, and thus the flow rate is controlled by partially blocking the met channel. This is done by either allowing the liquid to flow over the obstruction or under it. An obstruction that allows the liquid to flow over it is called weir. So you can say underflow gates. There are numerous types of underflow gates. Gates to control the flow rate, each with certain advantage and disadvantage. Underflow gates are located at the bottom of the wall, dam or an open channel. Two common types of such gates are sluice gate and drum gate. This is your sluice gate with this flow, and this is with the drum gate to control the flow rate. So you can also see when the gate is opened, the upstream liquid accelerates, it approaches the gate, reaches the critical speed at the gate and accelerates further to the supercritical speeds past the gate.
So you can see here it will act as a converging diverging nozzle here. So it will act as a nozzle. In the drowned flow, the liquid jet undergoes hydraulic jump and thus the downstream flow is subcritical. Also drowned outflow involves a high level of turbulence and backflow and thus a large head loss. The specific energy remains constant for an idealized gate and with negligible friction effects from point 1 to 2A. So this is your frictionless gate, which is the ideal case, and specific energy will vary from 1 to 2A. So there is no loss, but in actual case it will decrease. The downstream is supercritical for gate with free flow point 2B, but subcritical for one with drowned outflow point 2C. You can say in this case this is the energy 2B, and in this case this is the energy in case of drum gate. So in this case your flow become supercritical, that's why it shift to 2B, but in this case your flow remains subcritical, so that why in this case your energy will shift to 2C. Assuming the frictional factor to be negligible and the upstream velocity to be low, it can be shown that velocity is equal to 2G/1. The frictional effects can be accounted for by modifying this relation with the discharge coefficient CD. So then the discharge velocity at the gate and the flow rate becomes, so V is equal to CD under 2G/1. So this is your volume fluid CD A under 2G/1. The discharge coefficient is 1 for idealized flow but less than for actual flow for the gates. This is A, which is your gate opening. So experimental determined values of coefficient of discharge are given in this table, in this plot. So it versus a function of contraction coefficient, which is y2y, and depth coefficient, depth ratio, which is y1a. Note that the most value of CD for free outflow from a vertical sluice gate range between 0.5 to 6. The CD values drop sharply for downward outflow as expected, and flow rate decreases for the same upstream conditions. Now you can see this coefficient discharge is almost maximum for the free flow, and when you say it is for drowned outflow, it will decrease, it is less as compared to this case. So this is y1a, which is the ratio of, which is this ratio to this ratio. As this y1a increase, your coefficient of discharge will decrease. You can see